In this video, we will learn how to determine empirical and molecular formulas and through combustion analysis. So I'll be doing two problems in these videos. One, which is not combustion analysis, and the second problem is a combustion analysis problem. Let's look at the first problem. We have here vitamin C contains carbon, hydrogen, and oxygen as its three elements. And it is known that vitamin C contains 40.9% carbon and 4.58% of hydrogen by mass. And you are giving the molar mass of the actual vitamin C molecule, which is 176.12 grams per mole. And what is the empirical and molecular formulas for the compound? So first things first, when you have percent by mass, all the percent by mass of each element should add up to 100. Now, if you notice right here, I only have the mass percent for carbon and for hydrogen, but I don't have it for oxygen. So in this case, it becomes really easy, and I can say that the first step is we will determine the percent by mass of oxygen. And this is by subtracting the masses, the percent by mass of carbon and hydrogen from 100, because they should all hypothetically add to 100. So I can say that 100 minus 40.9 plus 4.58 equals to 54.52%. All right, now the second step is I will determine or convert all these percent by masses to grams. So I can say that I'll have for carbon, I have 40.9 grams carbon. I will have for hydrogen, 4.58 grams hydrogen. And then for oxygen, I have 54.52 grams oxygen. And then from here, I need to convert the masses to moles by dividing by the molar mass of each element. I'm just making room for myself right here. So I can say that I will divide here by the molar mass of carbon. And this should give me 3.40549542 moles. And for hydrogen, I will divide by the molar mass of hydrogen. And this gives me 4.534653465 moles. This is carbon, this is hydrogen. And lastly, I'm going to focus on the oxygen, and I'm going to divide by its molar mass, which is 16.00 grams of oxygen, and I get 3.4075 moles of oxygen. Now we note right here that we have now determined the moles, and we need to figure out the ratio between the carbon, hydrogen, and oxygen in vitamin C. So the third step becomes me dividing by, so I will divide by the least number of moles, and the least number of moles here happen to be the moles of carbon. So I will divide all the elements, all the moles of the elements by the 3.40549,542. Okay, and I will just keep copying and pasting this right here. So here's divided by this number, and then divided by this number right here, and I get a ratio of 1 to 1.3315693, and for oxygen I get 1.000588631. Now, note right here, I'll move just to the next slide because I'm out of space, that the ratio right here of carbon is 1 to hydrogen, which is 1.33, to oxygen, which is around 1. Now, I cannot leave the number like that in decimal, and we agreed to remove a decimal with 0.33 or 0.67. I will have to multiply by 3, and this right here gives me C3H4O3. So this becomes here the empirical formula. Now, I have determined the first portion of the question, the empirical formula. Next part is I want to determine the molecular formula. So the molecular formula is the empirical formula, which we already determined, which is right here, times N. And N right here is the molar mass of the molecular formula divided by the molar mass of the empirical formula. Now, the molar mass of the molecular formula is given to me in the question, which is the 176.12 grams per mole. Now, for the molar mass of the empirical formula, I can simply calculate it using the molar masses on the periodic table and then the number of atoms. So I will say that the molar mass of C3H4O3 is equal to 3 times 12.01 plus 4 times 1.01 plus 3 times 16.00. And if we calculate this number right here, we get 88.07 grams per mole. Now, so if we now try to figure out what N is, and I'm calculating this live with you, divided by 88.07, I get 1.999772908, and this can be rounded to 2. So in this case, I will multiply. So to determine I can write here molecular formula is the C3H4O3 times 2. So I will get here C6H8O6. Now, moving on to combustion analysis. And this is a problem where you have an aspirin tablet. Okay. And it tells you that the aspirin is solely consisting of carbon, hydrogen, and oxygen. And the mass of the sample and the initial mass of the sample is important because you will need it to calculate the mass of oxygen, which I will show you in a little bit. So 1 gram, so I will label this as the initial mass of sample. And it says you burn it. So burn it here indicates that this is combustion. Okay, and we collect 2.20 grams of carbon dioxide and 0.400 grams of water. And you are given the molar mass of aspirin, which is 180.16 grams per mole, and it wants you to determine the molecular formula of aspirin. Now, the beginning of a combustion analysis problem where you want to determine the empirical and eventually the molecular formula is a little bit different from the other problems because we will have to determine the mass of carbon, the mass of hydrogen, and we will use those masses combined to determine the mass of oxygen. So let's start with first step, determining the mass of carbon. So carbon is present in carbon dioxide, CO2, okay? And so we will say from CO2, and I will start with the mass given to me in the question. So I can say 2.20 grams of carbon dioxide, and then I will switch to the molar mass. I'll divide by the molar mass of CO2, because eventually I want to switch to the moles of carbon and then to the mass of carbon. Divided by 44.01 grams of CO2, and then there is 1 mole of carbon for every mole of CO2. And finally, I will switch to the mass of carbon using the molar mass of carbon. Okay, and I get here 0.6003635,537 grams of carbon. Now, the second step, I'll do the same exact thing to extract the mass of hydrogen. So I will say determine the mass of hydrogen, okay? And the mass of hydrogen can be determined from, or hydrogen is present in H2O, okay? So I will say from H2O, okay? Now, same deal, I will get the 0.400 grams water, divide by the molar mass of water, which is 18.02 grams of water. And then I will switch from the moles of water to the moles of hydrogen. I have 2 moles of hydrogen in 1 mole water. And then finally, the molar mass of water, of hydrogen, and then this gives me 0.0448390,677 grams of hydrogen. So now I determined right here, let me highlight the mass of carbon, and I determined the mass of hydrogen. Now note that oxygen requires a little bit of work because oxygen is present in both carbon dioxide and water. So the way to get over this is to take the initial mass of the sample. Let me go to the previous slide. So the initial mass of the sample, and I told you we're going to use this, is the 1.00. And I will subtract from the 1 gram the combined masses of both the hydrogen and the carbon. So I got 0.600 grams for carbon, okay, plus the 0.448 grams of hydrogen. And this gives me 0.3547973,786 grams of oxygen. Now, starting here in this point of the problem, it becomes very similar to the empirical and molecular formula problems that we've been doing with percent composition. Okay, so I will lay them out for you here. So I have So I will take the 0.600. I want to check again the 0.600. I think it's 0.600. I'm double checking it on my calculator. So we have here, let's calculate this again. I'm just double checking before I do my calculations. Okay, I actually got here 5.5999. Okay. got here point. Oh, or give me 1 second to double check it again. 4.01 times 12.01. I did indeed get the previous one. I apologize for that. So I got 0.66. So now I will copy and paste all these values on the next slide right here. So this is for carbon. So I will say for carbon, and then I'll copy and paste the hydrogen. Mass of hydrogen that I got, which is here. And then finally the mass of oxygen. Okay, and then from here, since we have the masses, I can switch to moles by directly dividing by the molar mass of each component. So right here, I'll divide by the molar mass of carbon, and this gives me 0.0499886389.5 moles. Same thing for hydrogen. And this should give me 0.0439511654 moles. And lastly, I want to make some room for myself. And then 1 mole of oxygen over 16.00 grams of oxygen. And this gives me 0.0221748316 moles. So this is carbon, hydrogen, and oxygen. And again, I will divide simply by the lowest number of moles. And just by looking right here, the lowest number of moles is for oxygen. So I'll divide everything by the moles of oxygen. I'm just going to copy and paste them to save time. Okay, and then here, divide by the 0.022, and then divided by the 0.022. Now, we will get a ratio. So for carbon, I got a ratio of 2.254295752. And then for hydrogen, I got 2.00204,936. And then for oxygen, I got 1. Now note here, this can be rounded to 2. This is 1. And I have a value around of 2.25. Now again, I cannot possibly leave it like that. So to get rid of the 0.25, I'll multiply everything by 4. Okay. And then this should give me 9, a value around 9. And this should give me here 8. Okay, a value around 8. And then here is 4. Therefore, the empirical formula is C9H8O4. Now, we want to now also determine the molecular formula. So molecular formula equals to the empirical, which is C9H8O4 times N. So it gives you here the molar mass of the molecular formula, which is here 180.16 grams per mole. And by calculating this value turns out to be also the same thing, which is 180. I'm calculating it with you, so it becomes here 180. This is the molar mass of the empirical is 180.17 mole. Therefore, the N here is almost 1, and the molecular formula becomes the same as the empirical formula. I hope this was helpful, and bye.